Hello everyone, my name is Chirag Patil and welcome back to my YouTube channel. So in today's video, we will learn what is variational autoencoder and how it works. Okay. So in our previous autoencoder video, we had understand how autoencoder works and what are the application of it, right? In that we had seen that there is one type of autoencoder which is variational autoencoder which used to generate new images similar to our training set, right? So if you want to see that video, you can check out my playlist. Okay, so let's understand what is variational autoencoder. So variational autoencoder is a type of generative models. Basically it is generating a new images, right? So it is generative model which is use the principle of autoencoder, right? So let's recap first autoencoder and then we will see how variational autoencoder works, right? Okay, so if you see this diagram, we had seen in the autoencoder session that autoencoder will take one input and it will compress our input into latent space, right here, and then the decoder will use this latent space and generate a image, right? Basically same image. Let's say this is original image and it will try to generate original image, in which our major task is to understand this representation, right? It also called as a latent dimension, right? Or you can say bottleneck feature, right? Okay, so you can use autoencoder in multiple ways. So this is just simple example, like input image will be your output image, right? And encoder will compress our image into smaller dimension and decoder will use that latent space and generate new image, right? You can pass here one noisy image as well for training and get the output of noiseless image, right? Or you can say clean image, right? So in that case, your autoencoder will be called as a denoising autoencoder, right? Similar application is you can apply one, let's say a black and white image, right? And train the autoencoder which will generate colorized image, right? So these are few applications of autoencoder, right? But if you see here, we are passing one image, we will get corresponding fixed latent space for this image and we are generating new image, right? So if you see this part, right, which is decoder, okay, so you can see decoder is working as a generator model. You can say it is generating a output based on this input, right, which is generated by the which is generated by the encoder, right? So decoder will use this latent space and generate this output. So basically decoder is working as a generator model. So how we can generate a new image while we, let's say I am passing this 6, right, and I want to generate a similar variation of 6, right? So how we can do? So that task is basically done by variational autoencoder, right? So let's see by the diagram. Okay, okay, so this is basically a diagram of variational autoencoder, let's say VAE. Okay, so encoder is same as our autoencoder. There is a decoder which is also same. The change is only this part, right? Let's understand what we are doing here. So let's say instead of generating a fixed latent vector or bottleneck feature, we will try to learn mu and sigma, which is basically mu is mean and sigma square is variance, right? So let's say we will try to predict mean and variance related to our input image, right? Okay, so if we receive or predict mean and variance, right, and if we generate a new vector using this mean and variances, right? So let's say, for example, if I say, let's say my latent dimension is, sorry, let me redraw. Okay, so let's say my latent dimension has a five dimension only. Okay, 1 2 3 and 4. Okay, so in autoencoder we will predict this exact value, right, for the latent dimension. But while we are implementing variational autoencoder, what we will try to do, we will try to predict mean and sigma for this each value. Okay, corresponding input, right? So we will find mu and sigma for each. So using mean and variance, we can generate a new vector using this mean and sigma, right? So we will generate a new sample from this mean and sigma square, which is basically variance, right? And that particular generated sample will be passed on to the decoder, right? And we will try that use this mu and sigma square. Basically we are predicting the distribution of each digit, or you can say each vector, right, for each element of the vector. Okay, so based on that distribution we are generating a sample, and that sample will pass on to the decoder, and decoder will generate output, right? And we will try that this mu and sigma square, right, this will follow a normal distribution, right? So we can help we can use it to generate a sample, new sample, and it will be helpful if you use normal distribution, right? So you will wonder why we are requiring this mu and sigma square and why we are using distribution here. Okay, so let's understand in the next slide. Okay, so this diagram is basically taken from the scikit-learn site. So let's say I am generating a vector. Okay, so let's say just for the what I say plotting purpose, my latent dimension is only two space, right? Let's say 2 digit, not 2 digit but 2 vector. Okay, let's say my latent dimension has only shape of 2. Okay, and understand, let's say this is 3, this is MNIST data set, let's say, and 3 4 5 and so on, right? 0 to 9. Okay, so these are the actual training point. Let's say for this point we are receiving 3, right? If I, let's say, select this point, right, because we are randomly sampling point, right, we know this mu and sigma square is mean and variance of that latent vector, and we are generating. So let's say we are receiving this point, right? This is not in the training set or testing set. Let's say this is new while generating a random sample. So this point will generate a new image which is similar to 3, right? But it is not the part of our data set, right? So for example, in the, let's say, if I say the example, let's say this is a cluster of digit 1, right? So here might be this kind of 1 would be there, right? If you see this part, this has this kind of 1, right? And if you see this, these are all the variation of 1, right? Someone write this. So if I select a point here, it will be a combination of these two somehow, but it will be 1, right? So it can be generated like this kind of 1, right? So it is a new image, you can say. If there is a MNIST data set, we are dealing with the image, so it will be the new image, but it will be most similar to our data set, right? So this is how variational autoencoder will utilize the mu and sigma square and generate a sample, and that sample will be used by the decoder, and decoder will generate a new image, right, or new data point. If you are using any tabular data set, so it will be new data point, right? So this is how it generate. Okay, so now you wonder what are the loss here and what will be our optimization function, right? So let's say, okay, so we understand two constraints, right? So first is basically we need our mu and sigma square to be normally distributed, right? Normal distribution. Okay, so loss is basically KL divergence loss. So this is the formula of that KL divergence. So what this do, it will return a higher value. Let's understand it as a loss. It will return higher value if our mu and sigma square is not following a normal distribution, right? If they are far from a normal distribution, and here let's say standard normal distribution or normal distribution, then this value will be higher. Okay, if this mu and sigma square follows a normal distribution, then it will be, or similar to normal distribution, then this KL divergence loss will be smaller, right? So KL divergence basically compare two distribution, how much they are similar, right? So we are comparing our distribution, which is mu and sigma, with standard normal distribution, right? So this is our first loss, right? And second will be our reconstruction loss. So reconstruction loss is nothing but, which we had used in autoencoder. You can use pixel wise MSE, right, mean square error, or you can say binary cross entropy as well for each pixel. So or variational autoencoder use the sum of these two losses, right, which is KL divergence, and second is reconstruction loss, which can be used like mean squared error, or you can use cross entropy as well, right? Okay, so there is one more thing. So let's say if you see here, right, as we say, we will receive mu and sigma square and we will sample, right? So if you directly sample, so here you will receive always random samples, right? Okay, so if you get a random value here, so back propagation cannot optimize it, right? Because let's say you are passing one forward pass, and at the back propagation you will get a random value every time, right? So it will not understand what to optimize, right? So what here we will do, we will use the sampling function like this. Let's say mu plus, let's say sampling is equal to z, right? So will be z will be mu plus sigma into, let's say, epsilon. Okay, so we will define external function which will calculate this epsilon. Epsilon will be nothing but standard normal value which is derived from the standard normal distribution, right? So you can say it is a standard normal variate. Okay, so we will get some value for the epsilon, right? And mu and sigma we are generating here. Okay, so when we are defining basically a deterministic function, so back propagation can go through this particular function, right? So in training point of view, we will train this mu and sigma. This epsilon will be external factor which will be not optimized, right? It will be not optimized. So our task is basically to find mu and sigma which is most near to a normal distribution, right? So if you use this formula, so we can optimize mu and sigma, right? This epsilon is the external factor. We will not optimize this epsilon, and epsilon is basically a random variable from standard normal distribution, right? So this is called as a reparameterization. Okay, so this is about variational autoencoder. Okay, yeah. So if you have any doubt related to this, you can write in the comment section and we can discuss there. In next video, we will implement this variational autoencoder using TensorFlow, right? So stay tuned. We will meet in the next video. Thank you.